Hi everyone, I am Srihari. I work at a company called Nilenso back in Bangalore, India. We are a software consulting firm, mostly do Clojure. Been doing Clojure for the last 5 years or so. We do a lot of functional programming in general. So this talk is going to be about my journey in making machines make music. And why I do this is because it's an intersection of two of my favorite interests. So I sing, I've been doing this for a lot of years, and I do computers. So I feel like this is a great place for me to do some really interesting, cool stuff. This is also all in the context of South Indian classical music. So a lot of this implies that this is recent work, and a lot of the research involved tends to be in the last 5 to 10 years or so. So that's interesting. I've been doing this for quite a few years, and so it's a hobby that's quite a long-term thing. And this process involves me rediscovering things I know intuitively about music, but understanding them from a machine's perspective helps me understand them deeper and in a different way. So that's something that excites me. I'm going to go over this in 4 phases, basically, and which is basically a reflection of my journey through this as well. And fundamentally, the theme of the journey is going to be about bridging the gap between humans and machines in how we make music and understand music. And within each phase, we'll be doing a cycle of synthesis, generation, transcription, modeling, and then back and forth. So that you're not left hanging, this is sort of what some manually transcribed synthesized music sounds like. Right, so right off the bat, you know it sounds quite a bit different. This is Indian classical music. I'll give you a primer into what all that's about. But before that, I want to talk a bit about how music is universal. So across cultures, across the world in different continents and from different races, we have fundamentally the same music concepts. So the notion of a tonic is well understood. Like everyone knows when a certain piece of melody comes back to the tonic, right? There's a certain resolution. Pentatonic scales are prevalent throughout the world. Like there's West African, Celtic, Indian, and Chinese music that all have a prominent major and minor pentatonic scales. And there's this famous Bobby McFerrin video of him jumping around and playing the audience, if you've seen that. And almost in all cultures, there's also a solfege of like, do, re, mi, fa, sol, la, si, or the Indian sa, re, ga, ma, pa, da, ni. And there are 7 notes in a scale, and there are 12 semitones in a scale, more or less. And everyone across the world kind of understands a lullaby, a sing-along, or a march song, or a hymn, right? So there's got to be something to this that holds it together and sort of brings everyone together, irrespective of where they're from and how they've thought about this. So there is a certain mathematical aspect to this that I want to uncover, right? There are pentatonic scales, there's the circle of fifths, and the harmonics. All that has a lot of mathematical symmetry to it. And there's the scientific process that we use to understand melody better, but there's also the physics of it, right? Overtones and harmonics and all of that. And of course, there's the art, where it's kind of melody and music is kind of inseparable from the person that creates it, and it's about creativity. But in the talk, we'll try to unravel what the mathematical and scientific aspects of melody are and try to understand them better. So the primer that I promised. So Carnatic music or South Indian classical music is what I'm going to be talking about. And I'm going to appeal to your human self and kind of let you take this music in rather than speak a lot about it. So that was a piece of violin extempore in a raga called Kalyani. But I think what I'm trying to get to is how it sounds fundamentally different from most Western music. It's not staccato. There's a continuum of notes. So very briefly, the instruments are primarily a drone called the tanpura, where we play a tonic and the fifth. There's a veena, that's the a lead instrument. It's also stringed and fretted, and there's a percussion instrument called the mridangam. And here's some visual understanding that I can give you of an ensemble of Carnatic music. Right, so you see that there's a primary vocal artist and there's an accompanist that's an instrumentalist or a violinist. There is a percussionist and there's someone sitting behind the main artist playing a drone or the tanpura. So digging in, it's classical music and it's art music in that the focus of a concert is music itself. It's not a part of a larger festival. It's not meant to be a form of entertainment or something. The intent is artistic. And it's ancient in that the oldest treatise on this, which is encyclopedic, is written in 500 BC. It's called Bharata's Natyashastra. So South Indian classical music is at least 2,500 years old, if not more. And there is, like every couple of centuries or so, someone comes by and writes a huge treatise in Sanskrit about the grammar of music at the time. And so that has evolved into a tradition called the Lakshana Grantha, and grammar texts. And it's an oral tradition in that my teacher teaches me something in class and I listen and I repeat, and that's the primary mode of learning. I don't write things down mostly. So in this age of digitization, if you're familiar with the Gartner hype cycle, of innovation and whatnot, Carnatic music is quite young, right? Which means that there's a lot of scope for us doing things in terms of digital transformation, and also presents a lot of challenges. It's also different from most Western music in that the nature is melodic, not harmonic. Indian classical music has little, if any, place for harmony. And it's all about creating melodic frameworks that help you create better melodies and sequences of notes. And there are certain concepts called ragas and gamakas, which we'll get to in a bit. And very similar to jazz music, it's mostly about improvisation. A concert is mostly about improvising in pockets around different renditions. And most renditions are covers of songs from like 2-3 centuries ago. So that's that. So entering phase one, this is me trying to take whatever I know of my music from my classes and trying to implement them in software. So I'll try and rush through this a bit quickly so I can get to the interesting parts quickly. So the fundamental abstractions. We'll go through the tonic note, a note, a raga, and I'll do a demo of the basics, right? So first is the notion of an adhara shadja, or a tonic, right? And this is, all the notes in Indian music are relative to this thing, right? So there is a notion of a tonic, and this is a choice of an artist based on their voice and their dynamic. And like I said, all the notes are relative to this. And it's just modeled as a number, right? A MIDI number. A swara is a note. It refers to the 12 semitones in an octave. There's a solfege, which is sarigama padani. That's what I say. And these form the elements of a raga, but so that it's more apparent to you, if you were to, it's just like an equivalent of a do, re, mi, fa, sol, la, si, right? So I say sarigama padani, except every time I say sa, or every time I say re, it might mean 3 different notes, depending on the context. And the context is a raga. And if I say ma, it can mean one of 2 things. And when I notate things, I write SRGMPDN. And so as a model, it's very simple. They are just relative numbers from 0 to 11, right? And they're all related to the tonic. And the sthai is an octave, basically, and there's a notion of a lower and higher octave, and this is just a reference of plus and minus 12. Prescriptive notation is what I write down in class and what is used to teach, and these are just written as the, 1 note per beat generally, and so that's what that is. So from here, I want to dive in and give you an understanding of the notion of a raga. And again, I'll appeal to your intuitive nature to understand this. Right. So what I would appeal to you to think about is the kind of emotion that this makes you feel, right? To me, this is a bit of melancholy, a bit of a yearning, right? And that's what a raga is meant to be. It's supposed to be a melodic framework that lets you evoke a certain emotion or a certain color, right? And it is a certain grammar that a composition must adhere to. And as a model, what it has is it has an ascension and a descension scale. And well, the first thing is that there are a lot of them. So you can see a count is 5,000 or so. Each of them has a name. And they're classified. So there's a parent raga, for example. The first one called Maya Madhavagaula is a parent raga, and it has a scale of ascension, descension. And it has a child raga, which is Gaula, which also has an ascension, descension. So quickly on that, the ascension and descension can be asymmetric. So for example, so that has 5 ascension and 7 descension, right? And then it can also be so for example, so there are like cycles there and whatnot, right? So they can be asymmetric and non-linear. So quickly on the demo, what we can do now is look up a certain raga, and this is Indic language written in Latin script, right? So it has to be phonetic. So you search by O-U-L-A, and it has to return G-A-U-L-A. And so you can play the scale, and then this sounds like this. Right, and then you can play a phrase in a raga, right? So, right? And so, for example, this phrase is in the context of a raga called Kalyani. Let me give you a better example. Right, so this is some prescriptive notation that is played in the raga called Bilahari. Now, what I can do is change the context of a raga to another one, and this is what it sounds like. Right? So now this is actually something that's mind-bendingly difficult for a human to do, right? Like take yourself out from one emotion and like transpose yourself into another one, into another grammar and another scale. But for a machine, it's stupid simple, right? Just want to think about that. With that, I think that's mostly what the basics are. Quickly, I want to give you an understanding of why I'm going into etymology at all. So I came across this very recently in that in Sanskrit, if you're familiar with that language, there is a grammar to create new words. And there is a grammar that lets you create new combinations of words or compounds of words. And this is a great, elegant solution to the naming problem in software. No more abbreviations and no more hyphens, prefixes, suffixes, right? You can create actual new words that mean the same thing to everyone who reads it. So in that context, there's a notion called, there's a swara, right, which is a note. So swara is actually swara, as in swato ranjayati, as in it shines on its own, and it's called that because it's resonant. So, and that is something that you can hear and you can relate to, as opposed to me speaking, which is also sound, but it's not resonant. And the raga itself means to die. It's derived from the word ranjayati. And well, it means a color, or it can also mean an emotion. And, well, so far we've managed to play some prescriptive notation, but that doesn't sound anything like Carnatic music just yet, right? It's still a staccato rendition. So in order to comprehend that, rather than keep all this in our head, into mellographs. So what you can do is take music and look at it visually in a much more tangible manner. You can take it, look at the shape, move it around, right? So for example, here's a phrase, and this is what the machine sounds like. Right? And that's the graph on the bottom. And if I were to sing this, right? right? So you see these small dips there above. That's not there in the machine at all. So if I were to take a longer phrase, what I sing will have a lot of curves in it, and what the machine has just steps, right? So there's no transition, there's no movement between the notes, like a continuum I spoke of earlier. So that is what a gamaka is. The interesting thing is that a gamaka is not something that I understand in theory, learning in class. It's something that I had to dig into to understand better. So it's an embellishment or ornamentation. Take, for example, so that you hear the twists and turns, and then there's a flick, and then there's a hook in the end. So that's how we refer to music in class and when we sing it. But these are not things that are easy to notate or have been notated. These are pervasive in Carnatic music, and every swaram is thought of as a continuum. And turns out they are actually names for these things. So spuritam, for example, is the one with the dip in between. A jaru is a gradual ascent or descent. A kampitam is an oscillation between two notes. So that oscillation is called kampitam. There's orikai, which is a spiral descent and whatnot. So if I had to dig in and understand what is really the difference here, if I take a piece of prescriptive notation, so it's like pa ma ga ga ma pa ma. So that is actually ma re pa ma. But I don't say 3 syllables, I just say 1. Right? So that's the gap that we need to bridge. And there have been some previous work on it, and I've left links in the references section, so I'm going to move quickly through this. So Gayaka is something that has a way to represent gamakas through some notation, and there's a database of phrases. So probabilistically, it would pick one gamaka based on a set of gamakas given for a raga. That's not scalable, obviously, because we'd have to write the phrases ourselves. And there's this work called Passer by Sri Kumar, which is basically a frequency envelope in the lines of ADSR and other envelopes. So this is pitch, attack, sustain, release. Each of them is a number, and they form a vector. And a single note can be described as a series of such vectors. So basically, it's a mathematical model for describing a curve or describing a gamaka. If I dig into this piece of literature 300 years ago called the SSP, or the Sangeeta Sampradaya Pradarshani, it has notation for each of the gamakas, and it has actually notated a whole bunch of songs with this. And with this, what I tried was using the notion of frequency envelopes and modeling something more generic, right? So I have, I can model a very easy dip with saying the frequencies and the durations for each of them, and I use a Welsh curve for each gamakam because that represents Carnatic music really well. And so I can use, if you look at the right top, there's a notation where I prefix each swara with the notation of a gamaka, and so this is what it sounds like now. Right, and now I have those dips. If you look at the melograph, you can see that there are some of those curves, and I was like, success. Now I can make music that actually sounds like Carnatic music. I also tried implementing Sri Kumar's Passer, and this is what that sounds like. Right, so that sounds great. And at this point, I was like, hey, you know what? I can make the machine make sounds like Carnatic music. And so quickly reflecting on what we've learned so far, there is a gap, which is the prescriptive notation is insufficient for reproduction. Raga as a framework itself is really powerful, and it enables the machine to do a lot more, and more than humans even. And melographs make melodies tangible for observation, and gamaka synthesis can be mathematically modeled as a curve. And the next part was like, hey, let me make some music now, right? Let me generate a stream of infinite music, right? I just want to sit back in my room and have the machine make, 1 hour of music based on my emotion for the day, and that'd be great, right? So what I failed to understand, though, is what other grammar exists out there that I can use. And to do that, I had to understand or look at melographs of music that's already out there, right? And so I studied that, and I was looking for patterns, and I want to infer the structure or more grammar to a raga from the information I saw. So a naive approach to generation would be just take swarams randomly from a raga and play them with random durations. So this is what that sounds like. Right, so that sounds like expected, pretty random. It sounds like something. It sounds like, you know, the pentatonic scale because that's what it's playing. But we can do better than that. So to study the data, what I did was I had to scrape the internet, mine it, because, you know, it's not yet digitized. And I had to mine multiple sources and stitch them together and then create an interface so that I can look at it in a meaningful manner and not just keep doing queries on the database. And then I had the ability to, like, you know, given a piece of raga, give me 50 renditions of these, right? And all this code is on a GitHub repository that's open source. And then now I have audio data, but I don't have frequencies. And turns out this problem is actually not that easy to solve. There are some algorithms that convert musical data or audio data into frequencies. Prat is one of them. What it does is it does autocorrelation and specialized for human voice. So once I do this, once I pass it to Prat, I have a mellograph. This one looks dirty, and that's real. All the mellographs I have of real music is mellographs of music from like 40, 50 years ago, and that's what is still out there, and it's not in like modern music format. It's all the music recorded as a single track from the audience. So that's like a lot of dirt there that I have to remove and all of that. But now what I can do is I can get a histogram of all the frequencies, right, of say 50 renditions of a given raga, and this is what that looks like. And I was like, wow, I can see my raga here. And what's interesting is like the highest peak is the tonic, and there's an octave after that, and somewhere in between there's the fifth. You quickly notice that not all the swarams have the same, all the notes have the same probabilities or same occurrences, right? And some of them are blunt, some of them are sharp, and there are actually reasons for this, and there are melodic reasons for this. And if I look at multiple ragas, I can see that they're different for instruments, they're different for fretted and non-fretted instruments. The left bottom one, for example, is an example of how dirty the data can be. And well, now I have pitch histograms, and this is valuable data, but I need to convert it into something meaningful. So I convert it into MIDI, right? Just approximate it to the nearest MIDI. But after doing this even, I don't have an idea of what a note is because it's all relative to the tonic note. And so I have to find the tonic, and turns out this is not an easy problem either. There is some popular work on this that involves a whole lot of digital signal processing and whatnot. And I figured, you know what, just pick the highest one and mostly just works. I did this across hundreds of soundtracks, and literally it was just sort by second and then pick the highest one and it works. And I have a swaram histogram, right? So I have my raga here, and it actually is what I want. You'll notice that the same swarams across different octaves actually don't have the same probability. And if I had to look at different ragas, even I have like a pentatonic and two other scales, and they're all different. And so now if I get back to generation, it's not so naive. So what I can do is, create a probability matrix and get the weight of each swaram and render that, and this is what that sounds like. Well, that sounds better, but it sounds like the background music for an 8-bit game, back in the day. And it doesn't sound anything like Carnatic music. And you see from the mellographs, based on random and the weighted one, you can see some differences in that there's lesser jumps, but there's still quite a lot of jumps, right? So what have we learned so far? We've learned that the tonic is prominent, of course. The fifth is also prominent, and the peaks are sharper, right? And they are higher. Other note peaks are blunt, which means that the continuums are larger there. And the probabilities are not all the same, and they're not same across octaves either. We can do better, right? So what I noticed is one thing, the Ragas grammar is not extracted yet, as in this doesn't take into account that the descension grammar might be different from the ascension grammar. So I want to derive that out, and I want to make it sound more continuous. This still sounds quite staccato and you know, discrete. So then, more generation, what I could do was, given that this is the note that was played, what is the probability that this was the next note that was played? And I can get this because I have the sequential data, and this is fairly easy to get. And what I could see was that adjacent notes probabilities are higher, right? So you now know that, you know, like sa to re is higher, and ga sa to ni is higher than, say, an octave shift. And from here, it was pretty easy, and Clojure lets me create lazy sequences, so I actually have a lazy sequence of notes that I can render. Awesome. And so this is what that sounds like. That sounds spooky, I know. But for what it's worth, the graph looks way better, and it does have a more continuous feel to it, and it sounds somewhat more Carnatic. So there's some synthesis aspects of this that I'm actually not going to talk about, but maybe another day. What I had realized at this point that I had stumbled onto Markov chains, right? So it's the first order Markov chains is what I had looked at, but there's of course the nth order Markov chains. So given that these were the 5 last notes, what's the next one that's going to be rendered? And like got all the better tools and whatnot, and try to make better music, but I hit a pretty hard dead end at this point because, well, the Markov chains, like even higher order Markov chains didn't actually sound a whole lot better. And I didn't know what to do next. But quickly reflecting on what we did, adjacent swarams are more melodious, and the sequencing per raga rules has now been kind of encoded because, you know, we have sequencing and ascension, descension, we have that. And there is a certain gamaka texture, right? And sometimes the in-between is far worse than the extreme. So this spooky music, some would say, sounded worse than the discrete music we had earlier. And that was actually a good excerpt. There are tons of really bad ones. And higher order Markov chains don't make it sound better. Again, a dead end. I did not know what to do, so I was kind of back to the drawing board trying to make things better. And some definitions of melody on the internet always used to say rhythm all the time, and I was thinking, well, I got to explore that. And there's repetition, of course, which is fundamentally, you know, psychologically something that we all really like and makes music more understandable and discernible. So I wanted to explore that. And I wanted to generate melodies, right, and understand tonal patterns better. So I dove a bit into the literature for this, and turns out it's fairly extensive. So Shruti Mata Leh Pita is something that it's an oft-quoted adage. So it means that pitch fidelity is the mother, and temporal discipline is the father. So laya means temporal discipline or tempo, right? And a change in tempo has communicative weight. I think you'd know this, right? Like if something goes fast and slow, it has a certain emotion to convey, right? So this makes me think that it has something fundamental to do with the notion of melody, right? And there's this other adage from the Sangeeta Ratnakara written in the 12th century. It says, Tala Tala Pratisthayamiti, as in Tala is Tala, as in bass. This is, again, an etymology where you can feel like, wow, I know where this is coming from, and so this is what it could mean, right? So it's hinting at something even far more fundamental. And the latter part of that says, Geetam Vadyam Tatha Nritam Yatha Tale Pratishtitam, which means that there's song, instrument, and dance are based on tala, right? You see how a notion of rhythm, if you can think about it like that, binds together song, instrument, and dance. It's kind of fundamental to all of that. But it's different from the notion of rhythm in that it's derived from poetic meter rather than dance. And the notion of a tala itself is a recurrent time frame, and it's a cycle of beats. And usually a tala is recognized as hand gestures, right? So 1, 2, 3, 4, 5, 6, 7, 8. And that's like the most popular tala. And it's used for conduction, right? So if I'm an artist, I have people sitting by me and looking at me. It's equivalent to the Western orchestra conduction. And then there's a notion of avartana. And avartana is one cycle of beats, kind of analogous to the Western bar of beats, but not really. But that's a closer approximation. And the interesting thing in South Indian classical music is that the number of beats per cycle often tends to be 3, 5, 7, 9. And these are things that even like a child going to school will learn all the time, unlike the normal 4, 8. And there are crazy talas like the Simhanandana Tala, which has 128 beats per cycle. And there's one called the Sharabanandana Tala, which has a very odd 79 beats per cycle. And there are actual compositions that exist in this and that are performed even. There are lots of other concepts relating to the notion of temporal discipline and Tala that I'm not going to get into. I will get into these three though. So a matra is a beat. Very simply that. Like every time I beat my hand, that's a matra, right? Like say 8 matras make an avartana. There's a notion of an akshara. Akshara itself means akshara, as in something that cannot be divided further, right? So that implies that it's probably the more fundamental unit of time that I need to care about and model, right? And there's a notion of a gati, which is actually gate. So if I were to illustrate 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So you know that there is a certain gate, and this factor that divides each beat into the sub-beat is called the gati. And turns out this factor is actually far more important than the matra or the akshara. And so with this newfound knowledge, what I can do now is go and make my transcription a whole lot better. So earlier, when I was doing Markov chains, I used to consider the 80 BPM and the 150 BPM song the same way. Now, I know how I can model that in a better way. I did a very clinical thing wherein, just sing the scale up and down. And for different gatis, I have different transcriptions. So for every beat, I have a certain graph. And every half beat, every 1/4, every 1/8 beat, I have a different graph. And now I can see things. What's interesting here is that at every half a beat, there is a certain structure that you can see, and this is actually the tonal structure. So if you were to listen to it, right? So you can hear the notion of pattern there. And the embellishments or the gamakas and the ornamentation is actually visible only at a much lower end of the spectrum. And you'll be able to hear that here. Right? So you were able to hear the embellishments. But the interesting thing is that once you listen to a lot of this, you'll notice that the tonal structure kind of disappears when you're listening to this. And so that's what is really interesting. When I dug into the textbooks, I found that the tonal patterns are actually at the beat level, or rather at the half beat level. This is actually quite analogous to what we saw with the prescriptive and descriptive notation back there, where humans actually understood prescriptive notation, but for a machine, you'd had to give it more detail. Similarly, we understand a beat, but what we're actually thinking intuitively is half a beat. That's what we can actually think about, but what we need for conduction is a higher concept, and that's a beat, right? And so we are able to see tonal patterns at half the beat, and embellishments, or alankaras, is what Sargnadeva calls it, and that's at the sub-beat level. And this is really cool, right? Because I now have names that I can use for things in software, right? Like, that's really the difficult part. You have something so abstract as a sequence of frequencies, right? And you want to deconstruct that into something and use that as a fundamental abstraction that you build other things upon and compose them. And having a name for something really makes that tangible. And of course, there was a lot of difficulty in getting here itself because the transcription is really hard. There's a lot of short-lived frequencies that are less than half an akshara, or the sub-beat. So remove those. Remove the non-prominent swarams in a raga because people sing inaccurately. It's not auto-tuned. And then there's the high and low cutoffs, because sometimes the autocorrelation picks up higher overtones and harmonies. You want to remove that because nobody sings 3 octaves higher than their tonic. And there are all these octave shifts that I found in the music that I was generating later on. And it turns out these were actually rests, right? So detecting a rest in music when you have a continuous stream of frequencies is actually not trivial, right? You'll have to look at how the pitch changes. And there's always a continuous drone playing in the background as well. So that was quite some hard work. But then, after this, if with this newfound knowledge of temporal discipline and modeling all this, I could revisit Markov chains because now I have input with higher quality because I know that I can use the data at different BPMs in the same way. And I have Markov chains at multiple levels of granularity because remember how we have 4 different graphs? Each of them can mean a different Markov chain. So for a single piece of music, I have multiple Markov chains. And I have so many knobs and toggles to play with. So for example, there is the order of Markov chain, there's the playback speed, and there's the speed on which the generation is based, and there is the synthesis mode, whether it's discrete or continuous, and there's the speed at which you play it. So if I were to take the generation gati of 4, where we expect the tonal structure, and then generate based on Markov chains at that level, this is what that sounds like. Right, so that actually sounds more melodious, and that makes me think that maybe that is Mohanam. And if I go lower to a generation gati of 8 and play that back at a higher speed, right, so that actually makes me think that, that's a tune, that I can actually use in a song or use for improvisation. And it doesn't really sound like Carnatic music just yet. It sounds more Asian, but I'm getting there, it's better. But what happens is, if you take a lot of Markov chains and a higher order Markov chains at the lower level, what you end up getting is a long chain of just embellishments. You can see how that's possible, right? Because you don't have tonal structure, you only have embellishment structure, and that's what Markov chains give you. And so you end up generating embellishments after another. So what I thought I could do was take the Markov chains at the matra level, or the part where I get tonal things, tonal structure, and then infuse it with embellishments. And this failed spectacularly. And this is because it actually depends on a larger context. So a tonal phrase can be ascending or descending. It can be ascending in the context that when it goes to the next note, it's going to stay up there for a while, or it's going to move away quickly from there. And the kind of embellishment depends on that, right? So you'd have to understand the patterns at broader and broader levels in order to understand what the embellishments should be at the lower levels. I'm still on that. I don't know how to model that very well in software. But what I did try out was this notion of repetition, right? So the word avartana is actually derived from the word avritti, which means to repeat or to recur, which was great. And this was like a mind-blowing moment for me because, hey, I was searching for a place where I can do repetition. And organic repetition is really hard because there are all sorts of different levels at which you can do repetition at a millisecond, microsecond, second, beat, multiple beats, bar, phrase, a line, an entire song. You can repeat all of these things and you don't know where to start. And this gave me a really nice place to start. And the very simple notion of repetition takes me to here. Right. So that actually sounds good, right? That sounds like a piece of music that one would use in a song somewhere, or like I can even use this generation to like help me with my own compositions maybe another day. But like I said, you know, like organic repetition is hard, and trying my hand out on that. Insights though, time is fundamental to melody. Modeling time in software is something hard. We often get this wrong, and this is a quite part and parcel of the notion of melody. Humans perceive more than a beat when hearing a beat. Machines understand tonal structures at half a beat and embellishments at lower levels. Markov chains don't work for embellishments, and the simplest form of repetition can be powerful. And in this process, I also have quite a few byproducts, which is, first thing, raga identification is a fad, which is that, you know, within 10 seconds of somebody playing some music, it'll be like, ha, this is that raga. And now my machine can do it too, because it's a very simple, you know, goodness of fit test. I have all this, you know, database of all the ragas, and I can say, given that these are the frequencies of tones I expect, what is this one? And then there's, of course, the notion that I can automatically notate music now. So take any piece of audio or like just sing into my machine, and the machine will give me the swarams that I just sang, which is really useful in education, really. And while I modeled all the Tala concepts, and I have not illustrated a lot of them here, I can now have an electronic percussion instrument. I can say what Tala to play in what speed, and it'll just play it back to me. That's really cool. But I mean, here's a nice existential conundrum that I often find myself in, which is that, you know, is machine music really music? Because oftentimes, to understand music or even to appreciate it, you have to get yourself into the feet of the artist to understand their expressions. And that's what's meaningful to you. You can't separate the artist from the music a lot, but you have to do that with a machine. And even if a machine comes up with beautiful music, is that still art? Right? So that's something to think about as you leave the room. But for now, I'll leave you with a piece of music that's human and still better. And I have here a list of references from the 500 BC to now. They're all links, and I put them up as a tweet or something. That's all I got. Thanks.